Alright everyone, let's start with the Laplace's equation this time around. It's a little bit different than what we've studied, and you will see that it's a steady state equation as opposed to unsteady equation, but it's one of the most studied of all the classical PDEs. That's something to highlight. We use this in fluid mechanics a lot. We use this in heat transfer. In here I'm going to focus on the heat transfer aspect of things. In the fluid mechanics, I have shown you in the earlier segment that I did the subsonic, supersonic, and hypersonic flows, and you've seen a relationship, velocity potential function, and that becomes a Laplace's equation. Okay, but let's go ahead and write the equation that I'm talking about: del square u del x squared plus del square u del y squared is equal to 0. So that's a 2D Laplace equation, and it's defined in this rectangular region. Okay, so the x goes from 0 to a and the y goes from 0 to b. And if I look at the initial conditions, how many initial conditions do I need? None, right? Because there's no time variance over here, so I don't need initial conditions. About the boundary conditions, how many do I need? I need 2 boundary conditions in the x direction. I need 2 boundary conditions in the y direction. So let's achieve that. So the first 2 boundary conditions is del u del x, the rate of change of temperature in the x direction at x is equal to 0 is 0, which means that this is insulated, and also my plate, if I'm assuming this is a plate, will also be insulated at x is equal to a. I'll plot this, okay? Just hang on one couple minutes. U x comma 0 will be equal to 0, so that's the bottom surface. U x comma b at the top surface, I'm gonna have f of x, right? So this is defined from 0y to b, right? Obviously, this is 0x to a. So let me draw this and I'll be right back, okay? We'll come back. So you can see in here what I did. This is the x-axis, this is the y-axis, and looking at over here, what you can see is when y is equal to 0, which is here, I have my temperature to be 0 at this particular surface. At the top, but that's what I meant by top, when y is equal to a b, it's f of x. This is the variable that we're gonna be able to use to get my Fourier series expansion coefficients, okay? But when I look at the x direction, this is now insulated over here, and this is insulated here. That's what this expresses, okay? So what I'm going to do now is I'll go ahead and solve this, all right? It's not going to be a very big surprise to you, but I will use the separation of variables. And exactly the same as before, except instead of t now I'm using y. It's going to be xx, it's going to be yy, right? And if I write my equation, it's going to look like this: x double prime y, because it's the second order, plus y double prime x is equal to 0. And I'm going to divide both sides by xy by xy. So when I do that, I'll say the x double prime by x plus y double prime by y is equal to 0. So if I move things around, I'll get x double prime by x is equal to minus y double prime by y, which is equal to my separation constant of lambda. Okay, now this will enable me to have 2 separate ODEs, and the first one will be x double prime plus lambda x is equal to 0. This will be a Sturm-Liouville problem, and it was the same thing in the wave equation, it was the same thing in the heat equation as well, so that's not a big deal. But the boundary conditions are going to be different because I'm specifying the derivative. Looking over here, I'm looking at the derivative in the x direction. Will be equal to 0, and the second boundary condition will be x prime at a is equal to 0. The right hand side also is insulated. Let's use another color. Y double prime minus lambda x is equal to 0, and this is actually easier. This one, y0 is equal to 0, you know that, and yb is equal to f of x, which I need to investigate. So I'll start with the first equation like I did many times. And when I start with the first equation, what I will end up with, I have to look at 3 cases. One will be lambda is equal to minus alpha squared, lambda is equal to 0, lambda is equal to plus, okay? Let's start with the negative, so that's typically what we do. Let's see, if you remember, we get trivial solution. I'm just curious, are you going to get the trivial solution? Because boundary conditions are different, okay? Just to highlight. Let's find out. And if I look at the ancillary form, you're going to get this solution to be c1 e to the alpha x plus, fairly easy, c2 e to the minus alpha x. And obviously the boundary conditions right over here is derivative, so I have to take the derivative of this with respect to x. So I will get c1 alpha e to the alpha x minus c2 alpha e to the minus alpha x. Okay, so then I will put x prime at 0 is equal to 0, so that becomes c1 alpha minus c2 alpha is equal to 0, because e to the 0 is 1, right? And e to the minus 0 is 1, 2. So from here you're going to get that c1 is equal to c2, so that's fine. So I have the c1 and c2 is equal to each other. Now I'll use the second boundary condition. C1 alpha e to the alpha a minus, I'm going to write c1 because they are the same, alpha e to the minus alpha a is equal to 0. And let's see, alpha c1s are common, e to the alpha a minus e to the minus alpha a is equal to 0, right? That's what I get. So from here, alpha is definitely not 0, because that's not the case. I have another case for that. So then either this is equal to 0, which doesn't make sense at all, right? A is a constant number, alpha is a positive number, so this can't be 0. So then the only way that then c1 will be 0. It's very similar to what I've done before, so I get the trivial solution. Okay, so as you see, the story seems to be the same as what we've been dealing with. So I'm going to skip lambda is equal to 0. That will be a big mistake, okay? As you will find out, you're not going to get trivial this time around. Don't do that, okay? It may hurt you. Alright, so let's do this one. So I have x double prime is equal to 0 this time. So x will be equal to c1x plus c2. Okay, fine. So let's prime x prime of x will be, well, c1 constant, right, the derivative. So f x prime of f0 is equal to 0, so this means c1 is 0. Okay. Okay, I said I'm not going to get trivial solution, but did I? Well, not really. I'm looking at c2, so I'm left with x is equal to c2. But let's double check that this actually doesn't conflict with the second boundary condition. So the derivative of this is, well, derivative of a number is 0, right? So it also satisfies the second boundary condition that I have prescribed over here. So this is actually a legitimate solution. It's just to say that in the x direction there will be no change in the temperature. Okay, it will be a constant value. So this is a non-trivial solution, all right? And let me do the positive one as well. And you can see that I have now this time I have lambda is equal to alpha square plus value x double prime plus alpha square x is equal to 0. Very similar. So from here you get x is equal to c1 sine alpha x plus c2 cosine of alpha x. Okay, so let's take the derivative. I will need this. X prime will be, well, it's fairly easy, alpha c1 cosine of x minus alpha c2 of sine of x, right? Okay, let's look at x prime of 0. So that will be alpha c1. What's cosine 0? That's 1, right? What about sine 0? Well, that's right, actually. Cosine 0 minus alpha c2 sine 0. So this is 0, so that goes away. This is 1. So you can see from here that I get myself alpha c1 is equal to 0. Alpha is not 0, obviously. C1 is 0. Oh, no. I'm still getting trivial solution, maybe. Well, let's look at the second boundary condition before we go too far ahead with our thinking. So if I do that, I will get myself minus alpha c2 times sine alpha a, right, is equal to 0. That's what it says. Well, I can say c2 is 0, but again, this will be the trivial solution. That's not going to be a proper solution. Alpha is not 0. So then the only case will be that this needs to be 0, right? So sine alpha a is equal to 0. So we covered this. This is now, it comes back to the eigenvalues. So if this is the case, alpha a needs to be n pi. So from here, alpha needs to be n pi by a. And n is equal to 1, 2, 3, and we'll go all the way to infinity. Okay? So these are my eigenvalues. And the corresponding eigenfunction for this case will be x is equal to c2 times cosine of n pi by a alpha. Why did I say cosine? Well, because you see this was sine, but then I'm writing, you know, the c2 belongs to this term, right? So I'm having this term turned out to be 0, this term still stays. So for that reason I'll have this, okay? So that will be my eigenfunction. Again, n goes from 1 to infinity. Now let's go to the second equation. This is the first equation. There is another one for the y direction, which I wrote over here in the purple font. So I will now have to deal with it, okay? So let's go ahead and deal with it. Like I said, I use purple font, so let's be consistent. I think this purple I used. So let's write this is equal to alpha square. So I'm continuing from this while I'm at there. Okay, y double prime minus alpha square y is equal to 0. Why negative? Why not positive? Because the equation up there had a negative in front of it. Okay, it's not my decision. So from here I get y is equal to c3 e to the alpha y plus c4 e to the minus alpha y. This is extremely similar to what I had for alpha is equal to a negative value case when I'm dealing with extraction. Okay, but this time on I have this boundary condition, not initial condition. So from here you will see that I'm going to get times e to the power of 0 is 1 plus c4 times 1 is equal to 0. So I get myself c4 is equal to minus c3, or other way around will work just fine too. So I'll have my y to be c3 e to the alpha y minus c3 e to the minus alpha y, and I have in ct parentheses e to the alpha y minus e to the minus alpha y. Okay, let's take a short information session over here. Sine hyperbolic x is equal to e to the x minus e to the minus x by 2. Remember that? So now I'll take advantage of that, and I will simply say that this y, let's go back, this y will be c, it's not the same thing as c3, right? And pi by a, which is my alpha, y. Okay? So you can see over here what I'm doing. So this actual c will be twice of the c3, right? Okay, so this was for the positive value, but I also have to care about when the alpha was 0, right? Or lambda was 0, right? So I get y double prime is equal to 0, so y will be equal to c5 plus c6y. So y0 is equal to 0. Well, then it gives me this c5 is equal to 0. That's what I get, right? So from here I get myself y will be equal to c6y. So now when or alpha is equal to 0, right, I get this. This is the extraction. Actually, let me underline this. And let's go over here. Where is it? Somewhere in the right here. This is. So the solution that I have, u, is x times y, right? U of x comma y will be xx times yy. So the xx was, so that was c2 times yy is c6y. So the combination of this, I'm gonna call this, well, a0. I'll get a0y. Why did I get 0? Because you obtain this when alpha is equal to 0, right? As I have an eigenvalue, so I'm trying to write this in the eigenvalue terminologies, right? So this is my x. So let's actually underline it with this pink as well, so it will be easier to see. And this is the y. So I have to multiply those two. Do you see that? X times y. Okay. So if I use the superposition as well, at the end of the day, I will get uxy to be this way. Okay. I will have a0 times y, I showed you. So now it will be from n is equal to 1 to infinity. Why? Because we defined this when as a positive value, right? So I will have an times sine hyperbolic of n pi by ay times cosine of n pi by ax. Alright, the next step is now to find what is a0, what is an. In order to do that, what we have to do is we have to go back to the original question, and we find out that, where is it? Right over here. I didn't even touch this set. Y at b is equal to f of x. So I'm going to use that to find my a0, an, alright? So let's just write it. Y at b is equal to f of x. So this needs to be satisfied for a0 and an to be found, okay? So if I go ahead and insert this, ux comma b will be f of x, well, that's what the question says, which will be equal to a0 times b, right, summation from n is equal to 1 to infinity, an times sine hyperbolic n pi by a times b, not y, cosine n pi by a x stays right there, okay? So now I will actually write here, you may have seen it already, some of you, but this is a half-range Fourier cosine expansion with this becomes lowercase a0, this becomes lowercase an, okay? Let me explain this for those of us who didn't see it just yet. So Fourier cosine series. So let's take a look at it. F of x was a0 by 2 plus summation n is equal to 1 to infinity an times cosine and pi x by p, where a0 will be 2 by p, 0 to p, f of x dx, and I had this a sub n is equal to, again, 2 by p, 0 to p, f of x, but now I multiply this by cosine and pi x by p dx. My goal is to look into this, this equal to that, right? So you can see an a0 is here, so I'm going to equate this to here to find, as a function of f of x. And you can see f of x are the same, letters that we designate, okay? And I'm looking at the second one. You can see a lowercase an times cosine. One thing is p is a. You see that, right? P is a everywhere. So this becomes lowercase n, which basically becomes here. I'm going to take this, plug it into here, and find, okay? So that's the process that I'm going to take. So let me do what I just said. Let me go back to the other color. And P is A. That is something I would like you to have in your notes. A0 by 2 is equal to capital A0 times B. So from here, you can see that A0 becomes 2A0B, which also, looking here, I'm just going to plug it into here, okay? That will be 2 by A. Remember, P is A. 0 to A. F of x dx. Looking here, I can cancel the 2's, and if I do this, my a0 becomes 1 by a times b, right? Integral from 0 to a f of x dx. So that's it for a0. I was able to find a0. I go back, so I was able to find my a0. Now I'll do the same treatment for this an. Remember, this is lowercase a sub n, okay? So if I do that, capital an times sine hyperbolic n pi by a b will be equal to lowercase an, and up here you've seen over here, so I'm just going to take this and plug it into here, okay? Except that I'm going to replace wherever I see p with a. 0 to a f of x cosine and pi by a x. Let's not forget the dx, okay? So I simply get nothing, not nice, but 2 by a sine hyperbolic and pi by ab. 0 to a f of x cosine and pi by a x dx. Okay, so now I'm done. I'm not going to rewrite it because it's been a long segment, but a0 I calculated, an I calculated, that's it. This is what the final equation is, and where a0 is this. Okay, let's actually do this. Where an is this, and this is the main equation. So that's it. You see, those are the three important ones.